So yeah, to wrap up, so we're gonna finish up WKB. And the last time we sort of showed the WKB solution in general, valid for when the behavior of your system is classical for slowly varying potentials at high momentum. And we'll see why it's slowly varying sort of in a bit, but this was the general solution. Let me just write it in terms of these Q's, and then I will rewrite it in terms of quantities that you're sort of maybe more familiar with in terms of the wave vector, the kind of equivalent wave vector for the problem. But generally speaking, it was these guys. A is some kind of place where we start to evaluate the WKB solution, and usually it's a classical turning point. And in these rescaled units, it's we had defined this quantity Q, but we can connect it back to things that we're more familiar with, in particular Q over delta. If you go back to definition of Q, it was, and delta, it was the rescaled, it was the energy scale, the length scale divided by h bar, that's from the delta. And then the Q part was the rescaled energy minus the rescaled potential. So the factors we introduced all just kind of cancel it out, and you just get that it's square root of 2m for h bar times this length scale, and then it's square root of the difference between the energy and the potential. And that is nothing but the length scale times an equivalent wave vector. All this stuff, if we had a constant energy, constant potential, this would just be the wave vector associated with potential energy. So, and this is a function of the coordinate z. So yeah, so that's what Q is. And so you can also just substitute in, instead of Q over delta, you can just put in this wave vector. And of course, Z, remember, is just the coordinate divided by L. So you can also just restore the coordinate if you wanted. But the point is, what we saw is that these solutions, we know that when we go from a place with positive kinetic energy to negative kinetic energy, the potential looks like a linear function. And so what we ended up doing is solving the Schrodinger equation for a linear potential, basically. So that's where we left off, and that's how we got the matching conditions. We saw that the Schrodinger equation in the rescaled units, we could write like this. Where W is related to our coordinate Z, alpha times Z minus Z naught. Z naught is the location of where we go from positive to negative kinetic energy. And alpha was related to the slope of the potential near that turning point. So this was like that, where G is just what the slope is of the potential. It was Q squared at around Z was approximately minus G, Z minus Z naught. It's just the slope. So that's a differential equation you can solve. You get the area functions, and you can look at those area functions far away from the turning point. And so that gives you solutions that are in the, the positive kinetic energy and negative kinetic energy regimes, classically forbidden and classically allowed. And by using those area functions, you can match the solutions across such a region. So then after solving this, we did the matching, which again matched up those two regions. So if in the classically allowed region, where we have positive kinetic energy, we would get oscillating solutions. Or better yet, if we start in the classically forbidden region, say, where we have the exponential solutions, right, exponentially growing and exponentially decaying, then these are what the solutions look like. So there's different kinds of turning points, right? You can go from forbidden to allowed, or vice versa. So I'll just write down both kinds. You can also go from, it could be the opposite situation, right? Where on the left, you have an allowed region. Again, you always think of it as positive or negative kinetic energy and oscillating and decaying versus exponential solutions. So you can have the reverse as well. And that's just two different kinds of potentials, right? Either the linear slope goes one way or it's negative slope and goes the other way, but it's still the same area functions. There's no difference there. Yeah, so, okay. So for the condition where it's forbidden on one end, we have the following, right? We have these solutions, the exponentially. No, my dog's pretty upset today, but he didn't like. So, okay, we have the exponential decaying solution here. And again, I put the Q bar because that's the, Q becomes a pure imaginary. So we define Q as I times Q bar. Again, it's the same as that difference between K and kappa that we looked at in the first semester when we studied problems like this, the one-dimensional Schrodinger equation. And then all right, and then for the exponentially growing solution, we have this. And then the point is you can use those area functions to match up what happens in the other region. And so on the other region, you would normally just have two coefficients, C3, C4, with the oscillating solutions, right? E to the I, Q, right? E to the plus or minus IQ. But because of the matching, it's like matching the derivative and the continuity, except you actually have to use the area functions to match across the Z naught boundary. What you get instead is that instead of just the plus or minus IQ stuff, you get different combinations of them that match up to these coefficients C1 and C2. And the combinations are C1 over Q. And now Q is, the wave vector equivalent. And we get cosines, which again are just combinations of plus or minus IQ, right? But it's the appropriate combinations that, let's see, make sure so if Z is negative, sorry, yeah, we integrate from Z to Z naught. So this should be Z. To Z naught, Z to Z naught. And then in the other region, we go from Z naught out to Z. And this just becomes Q over delta. This is the cosine. Again, we got some integration here, and then we have the signs. And the signs, there's a phase factor, there's a minus sign that comes in, but otherwise it looks like this sign, z naught to z, q over delta. And there's a minus pi over 4, which again comes from the asymptotics of the Airy functions. But I'll show in recitation today another way to derive these matching conditions that doesn't make use of the Airy functions, that just uses the idea of analytic continuation to do it. So if you're interested in a sort of more transparent way, but that uses slightly more sophisticated math, you could check out the recitation. But let me just write down the rest of these. So this is, let's see if I have this right. So, okay, we have the exponentially decaying and growing solution, and then we have the two oscillating sines and cosines. So now you see you only have two constants here. So you can get the constants just by boundary conditions on your whole problem. So whenever you have any kind of turning point, you know how to match across that turning point. And so the rest of the problem you would just get by, applying the appropriate boundary conditions. And there's all kinds, we can look at scattering problems or bound states, anything like that. Yeah, so so let's write down the other kind of matching problem, which is if we go from an allowed region to a forbidden one. So that's, let's see, that's sort of the opposite. You start with these cosines. And again, so this is z to z naught. Now the opposite kind of, I'm not going to put the variable of integration, it should be pretty clear. So here it's cosine minus pi over 4. And then it's minus C2 over square root of Q, sine of the integral, C to Z naught. Yeah. Oh, sorry, I'm missing a minus pi over 4 here too. There's always the minus pi over 4. It's a phase shift that you get when you do the matching. And this is sort of similar, minus pi over 4. And then on the other end, you'll get C1 over 2 square root of Q bar. And these are the exponentially decaying solutions. And this time it's from Z naught to Z of Q bar. And the other one is C2 over Q bar. It's the exponentially growing solution. So it's 1 over delta integral of Q bar from Z naught out to Z. Okay, so that's it. Let me see if I can get all these coefficients right. I think I have, yes. So these are the two kinds of turning points. There are no other kinds. You either go from forbidden to allowed or from allowed to forbidden. And that's it. And these are the WKB matching formulas. Remember I promised I would tell you about the slowly varying condition. And remember that the equation that we started with for getting these solutions in terms of a perturbation was, we started with a substitution into the wave function and found that after substituting psi like this, we got a differential equation which was of this form. And we assume that this term is small. So, and that's the fact that that term is small is what makes this approximation a slowly varying one, quote unquote, we have to ensure that the magnitude of this term is much, much smaller than, the term that we leave behind, which is 5 prime squared there. And so what that means is, of course, phi prime, remember that to leading order, we saw that phi is the integral of q dz, so phi prime is just q. So to leading order, it means that delta phi q prime must be much, much less than q squared. That just comes directly from this condition. And if we were to plug in what this is in terms of the wave vector, it just tells you that dk dx is the magnitude of that. I guess I should still keep these magnitudes around, is much, much less than the magnitude of the wave vector squared. Remember, the wave vector is that difference between the energy and the potential. So that's what it is. That's the sense in which it's slowly varying. These derivatives, this is a condition. Again, this is a condition on the slowly varying nature of the potential, right? Because K is, as I said, related to the square root of the energy minus the potential. So if K is slowly varying, then the potential must be slowly varying in this sense. And this is the regime of the validity of the WKB. So we can actually do an example of a kind of problem you could apply this to. Typically, this is used for, you can use it for any 1D Schrodinger equation, and then that spherically symmetric Schrodinger equation, you can also convert that to a 1D Schrodinger equation by just using the radial coordinate. So you can use it for any kinds of problem like that. But it's most often used, I guess, to construct bound states for, certain Hamiltonians that you don't know how to solve exactly. So for a bound state, we imagine a situation like this where you have some potential and your energy is like this. So you know that you go from, there's 3 regions, and you go from a forbidden to an allowed region to a forbidden one again. So you know what the solutions look like in those 3 regions, and you know what all the matching boundary conditions are because of the matching formula. So you can actually just write down what the solution is immediately for the wave function. So we can suppose that this is at some point A, and this is at some point B. This is as a function of this rescaled coordinate Z, say. Again, the red is the potential, the blue is the energy. So we know what the solutions look like in every single one of those places. If out here for Z is less than A, we would want the solution that exponentially decays. So you have to use that boundary condition we normally use for bound states, that the wave function goes to 0 far away, because then it's going to be square normalizable. So you got square root of q bar, and we've got this exponential solution. It's the one with the minus sign, because we're going to integrate from let me think. Yeah, we're going to integrate from Z to A. So the integral is positive. So we want to make sure that everything in the exponent is negative. I recognize that Z is negative, or it could be, but it doesn't have to be. It's just from A to B. But we pick the minus sign there because we want to make sure that it decays exponentially with as Z becomes sort of more negative this integral is a positive integral, right? Because Q bar is always positive, and we integrate from Z out to A. So we integrate from left to right. So the integration is going to give us a positive number. So that's how you can check in your head to make sure that, you have the right sign for things. And then, of course, we also have the stuff that's out here, the stuff from out in the other forbidden region. We know what that is. That's going to be some other C1. I'm going to call it C1 bar, say. And that's 2 square root of Q bar. And that's another decaying exponential. And that's going to be the integral from B out to Z of Q bar. And it'll be like that, right? So that's the other forbidden region. So then in the middle, you know that we can match. That's the classically allowed region. We can match. And which one we use to match either A or B, it doesn't matter. They both have to give us the same result, right? Because it's going to be the same function in there. So that's the beauty of it, is that because it has to match with at B and at A, you get 2 different solutions in the allowed region, and those 2 solutions have to match. The first one is C1 over square root of Q bar. That's the cosine. So there is no C2. So the C2 part drops out, and you just get the cosine integral from A to Z Q over delta minus pi over 4. Again, I dropped the variable of integration there just to make it a little more compact. And this has to be equal to C1 bar over square root of, oh, sorry, there's no bar here. This is a classically allowed. So bar is for classically forbidden. So this is over Q. And this is cosine of Z to B of Q over delta minus pi over 4. Now you see the limits of integration are different, right? In one, you go from A out to Z, right? For one of the matching conditions, and for the other condition, you go from Z back out to B. So the limits of integration are different, but those 2 solutions have to match as a function of Z. So we can actually use that to our advantage, the fact that these 2 things are equal. So first of all, yeah, so we can actually use that. So the first thing to recognize is, of course, that the constants have to be the same, the C1 and C1 bar. So then we have to just make sure that those integrals somehow give us the same result. So that's what we're going to check. We're going to use this equation. Any questions, though, before I do that? No? Okay. So we're going to take the cosine, which is the integral from A to Z of Q over delta. I guess I can restore back the variable of integration if I want, minus pi over 4. And now this thing, we're going to, again, we're going to have to set it equal to the other expression, and we're going to do it in a kind of clever way, or we're gonna sort of see how to do that, and we're going to do it by just messing with the integration a little bit. So what we can do is we can break up this integral. We can introduce a intermediate value B along this integration from A to Z. We can rewrite this as follows. We can say that, well, this is an integral from A to B right? Q z bar over delta dz bar. And then we're going to add to it an integral from b to z, right? Or alternatively, we can flip the integration limits and write it as an integral from z to b instead, right? I can either, this is the same as doing plus integral from b to z. And I can do that because I can integrate from a to b and then from b to z. That won't change anything there. It's just breaking up this integral in a clever way. We're doing it in order to kind of reproduce this kind of integral from z to b. And we can do that by just breaking up this integration from a to z to one from a to b and then from b to z. But again, with a minus sign there when we flip the limits of integration over. So this is it's just an identity, just messing with that integral. And then we're also going to mess with that pi. We're going to say that this is plus pi over 4 minus pi over 2. And again, altogether, it's just minus pi over 4, which is what we started with. But this is nice because cosine of something minus pi over 2 is the sign. It's just the sign of that thing. So this whole thing is going to be the sign of the integral from a to b. So again, what we're doing here is we're trying to get this cosine part to look like this cosine part. And then we're going to see what we can do with this equation, with this equality. So that's the objective. We're just massaging things in order to get out that cosine from z to b. But it's not so easy. We have to go through some trick to do that. So, okay, so you have sine of q over delta z bar, and then we have minus, and now I'm going to rewrite this minus as minus the whole quantity from z to b, q over delta z bar dz bar minus pi over 4. Right, I'm just extracting out a minus sign, and now I can use the angle addition formula for sines of things. So there's a sine of, sine of the sum of two angles. That's just the sine times the cosine of the two angles minus the sine and cosine of those two angles flipped. So this is sine of a to b qz bar over delta dz bar cosine of this stuff now, z to b q over delta minus pi over 4. Again, I'm dropping that limit of integration. And then we have the other term. So you have minus cosine of integral from a to b q over delta and sine of z to b q over delta minus pi over 4. Okay, so now we have to take a look here and see what happens. So we see that this cosine here, we can rewrite it as a sum of two terms. One is proportional to the cosine of the same cosine that we have on the other end. This cosine right here. So I misspoke a little bit. We know at the very least that C1 and C1 bar are constants, but they're not necessarily equal. They won't be equal typically, or actually they won't. So, but we do know that this cosine at least has to be proportional to this cosine right here, and we just show that we can rewrite the cosine on the left as a sum of two terms, one which has that cosine that we want, this one of the double line. It's exactly the same cosine, and something that we don't want, a sine of this. So we don't want this. We don't want that because we know that this cosine must be proportional to this other cosine. So we can't have any additional terms like this. So the only way that this matching works is if this term here, the second term, vanishes. And the only way that that's possible is if this thing out here is equal to 0. This thing won't generically be equal to 0 because z is a variable. So, you know, it would have to vanish for all z. So that's not going to happen. And yeah, so the only way that these two solutions can match here is if this term vanishes. And this is just it's just a cosine of a constant. It's just an integral with no variables left over. It's just an integral from a to b of q over delta, you know, integrated over that entire classically allowed region. So this has to be equal to 0. And the only way this can be equal to 0 is if everything in here is equal to a half integer multiple of pi, right? Because the cosine only vanishes when you're at like pi over 2, 3 pi over 2, and so on. So you see, well, you know, 1, 2, 3, and so on. So this gives us a quantization condition on the energies. Because recall that q over delta is nothing but the wave vector, which is square root of 2m over h bar squared square root of e minus v. And so that means we have a quantization condition. And in fact, again, we can call the wave vector the momentum over h bar. And this, yeah, so, and this we can actually write in terms of the regular Planck's constant without the h bar. It's this 2 pi momentum, right, divided by just regular h. So what we found here is that 2 pi over h, the integral of p from between the two turning points, that has to be equal to n plus 1/2 pi. So this is nice because the pi's cancel. And moreover, if we think about this integral 2 from a to b, this is the same as integrating from a to b and then back from b to a in a loop. So we can write twice the integral from a to b as a loop integral around back and forth across the from sort of one turning point to the other and back again in a loop with the, you know, the direction defined along the loop direction, just so you get a positive number for both directions. So we can, this is actually a loop integral of p z bar, where the loop goes from one turning point to the other one and back again, just around there. That gives us twice that integral from a to b. And that's equal to n plus 1/2 h. And this is called the Bohr-Sommerfeld quantization condition. And, you know, maybe early on in your, you know, in the early days of quantum, This was a kind of a heuristic way in which people got, say, energy levels for electrons. They would say, okay, imagine an electron in some orbit, right? Then we know that it has some associated de Broglie wavelength, right, associated with its momentum. So that wavelength has to fit inside the orbit. So if we integrate around the orbit, then we should get an integer number of de Broglie wavelengths in there, and that gave people a way of calculating a quantization condition on the energy levels. This is the exact derivation starting from the Schrodinger equation in the sort of semi-classical regime. It shows you when that kind of heuristic argument holds. This is precisely when it holds, is when you can do this kind of semi-classical analysis, and we see we get the same kind of result that we might have guessed, from just thinking about de Broglie wavelength fitting inside an orbit or something like that. So it's sort of it's a nice thing. It's WKB gives you a way of sort of precisely identifying when these kind of more heuristic things that people used to do sort of at the beginnings of quantum mechanics to derive quantization conditions. And it gives us a mathematical handle for the validity of such heuristic ideas. Now it's not heuristic. We know exactly where it comes from. It comes from, just from Schrodinger's equation in the limit where you have a slowly varying potential. And so this is now more precise. We don't have to, think about orbits or anything. We just are we are given a potential. We look at the energy. We identify the turning points where the energy hits the potential, and in the semi-classical limit, the integral between those turning points has to be quantized in this way. And yeah, and then depending on the kind of boundary condition, if you have like an infinite wall for the potential, things like that, you might get other kinds of quantization conditions. But you don't know how to do this because, as I said, you have everything you need in the matching conditions. For any kind of turning point what the matching conditions are, and then you're left with these two constants, C1 and C2, and those you can fix, however you need to fix in order to match the boundary conditions that you want. So in the homework, you'll be doing a scattering problem, right? So you identify the turning points, and then you identify your boundary conditions. In the scattering problem, you want your incoming plane wave, right? So you'll have to arrange so that these coefficients in the allowed regions, C1 and C2, right, that you form the right combination of them such that they add together to just form the incoming plane wave, for instance, the e to the I kx kind of thing. But with these matching formula, you now have sort of everything you need to do any kind of problem like that. You can, for any kind of potential. So here, for instance, would be a scattering one. If you have something like this, say you want to compute the scattering from some kind of guy like this, right? What would you do? Well, you would, maybe if you have an energy like this, you would identify the turning points. You would know the solution in this region in terms of, C1 and C2. Out here, you would have a classically allowed region. So you want to combine your C1 and C2 coefficients such that you only get an incoming plane wave, which has the form, e to the I kx. And out here, and well, I guess there could be reflection. So actually you would want to keep both the sines and cosines arbitrary, but you want to rewrite them so that you can identify which one is reflected and which one is the incoming part. So you want to get the right combinations, and for scattering, the right boundary condition is that there's no wave coming in from positive x, right? So you just want one outgoing wave. There's the incoming, there's the transmitted, and the reflected. So you set up those C1, C2 coefficients out in regions 1 and 3, right, to match what you want, the boundary condition. And then everything else you know how to do because you have those matching conditions across any turning points. So, you know, this for instance, this kind of turning point goes from classically allowed to classically forbidden and vice versa. So you would just look up, you would go to your formulas, which, you basically have to memorize, I guess, or, know where to look them up and just recognize, oh, well, I'm matching from allowed to forbidden. So I would use these matching formulas, right? And of course, I would, again, choose the C1s and C2s appropriately so that I get the incoming and outgoing, the incoming and reflected waves. So I'd have to rearrange the C1s and C2s, right? So that I can rewrite that expression as e to the I kx and plus, a reflection coefficient e to the minus I kx. But you know how to do that. You just expand the cosines and sines and complex exponentials, right? So it's not too bad. So that's the idea, is that these formulas are like the generalizations, I guess, or something of for arbitrary potential shapes, slowly varying potential shapes of what we would have done if we had like a piecewise constant potential, right? We're used to that, like a step function stuff. We know the solutions there are just, e to the I kx or e to the plus or minus kappa x. Here, it's just a generalization to a slowly varying potential where instead of just having kx, you have an integral instead of k, essentially, with a prefactor, the square root. But other than that, the nature of these solutions doesn't really change. You have either oscillating things or you have exponentially growing and decaying functions. So you can still build your intuition by just drawing pictures of what the solution should look like this. Still, basically like this, except instead of k's, you have integrals. Any questions about that? Hopefully you see the sort of how this can be quite useful in a practical situation. Okay, if there are no takers, we can sort of move on to the next topic. But hopefully this made sense to you, right? It's the same stuff we did last semester, even for this guy. We have 3 regions. We could have done the same thing, with matching the boundary conditions, right? We have 2 unknowns here and 2 unknowns here, and we drop. Again, you just count up constraints. So at each turning point, we have 2 equations essentially, and we have 2 unknowns in each region. So, and then we have, of course, the wave function normalization. So in the end, what do we have here for a bound state? We have 2 unknowns out here. We have 2 unknowns in the middle, the C1s and T2, and 2 unknowns out here. And so that's a total of 2 plus 2 plus 2, 6 unknowns. Then we have how many equations? 2 plus 2, 4 matching equations. Then we have 2 boundary conditions where we say the wave function can't blow up at plus or minus x. And then we have 1 normalization condition, that the wave function is square normalized. That gives us the overall constant in front of the wave function. So how many total conditions is that it has to satisfy? Is 2 plus 2 plus 2 plus 1 is equal to 7. So that's 1 more than the number of unknowns. So we know that something else must be constrained, and that's, of course, the energy. the energy is quantized. So it's the same story. It's just slightly generalized to something beyond just piecewise constant potentials. But in fact, I don't know if you remember, I think at some point we talked about looking at, yeah, I think we did. I think you go back to the notes and you look at, I actually did a problem like this, like transmission over an arbitrary shaped barrier. And I talked about, what you could do there is you could approximate the barrier as a series of potential steps like this. And then you integrate over those, you can integrate the sort of transmission across all these little steps. If you go back to that in that first semester, just for your own curiosity, you'll actually see that the formula you get is just essentially the WKB one. But anyway, that's a little bit of a connection, but to the last semester, but it's not that important. Okay, any questions? Key formulas are, of course, these guys. Again, this is basically like the generalization of matching the derivative and the continuity condition that we had for piecewise constant potentials. Okay, I'm going to clear then. So there are no. So the next topic we're going to talk about is time-dependent perturbation theory. And this will lead us into a discussion of, how to deal with time dependence sort of more generally. But again, the idea is your Hamiltonian is some Hamiltonian quite well, call its eigenvalues and eigenvectors. And then your perturbation now is small, but also happens to be time dependent. And this should remind you vaguely of the Rabi oscillation problem we did, where we had an applied magnetic field that was oscillating. It had some time dependence. There, we happened to know how to solve the whole problem exactly. But imagine you didn't know how to do it and you had to treat W perturbatively. Well, then, you might be in some trouble, right? If you don't know how to solve it exactly, you have to figure out some way to do it as a, a power series in lambda. But to begin with, we're going to first derive a kind of heuristic formula that you can use in these situations, which is called Fermi's golden rule. And oddly enough, he didn't actually he didn't derive this. It was like Planck or something. He just called it his golden rule, and then people just decided to call it his golden rule, but he just called it that. So maybe if you pick a favorite formula or something that you like and start calling it your golden rule, maybe it'll be eventually named after you. But it's not, you didn't derive it. So what is it? It's a way of calculating transitions, probabilities of transitioning from one state to another one under such perturbed Hamiltonians. It's, it's the probability of observing your system in some final state F, supposing it evolved under, this time-dependent Hamiltonian where, your initial state was some initial I. It's a way of calculating this probability. And the way we begin is, as usual in perturbation theory, if we use what we know, and we know this. So what you would begin with is you'd say, okay, fine, I know the Hamiltonian. I know it's eigenvalues and eigenvectors. So I can expand, of course, any state as a linear combination of eigenvectors of H naught if I wanted to. And so I can also, of course, expand the whole Hamiltonian. I can define matrix elements of the whole Hamiltonian in terms of the eigenstates of H naught. And these will just be, of course, the energy eigenvalues, you know, stemming from the H naught part. And then there will be some matrix elements, some time-dependent matrix elements that give us the perturbation, right, with the lambda. So what we do now is, of course, we want the time evolution, so we need to solve, you know, the time-dependent Schrodinger equation. So we have the usual thing. And now we just take these ideas, right? The fact that we can expand the state and the we know what the matrix elements are for well, we don't know what the W's are, but we'll just leave that alone for now. Then we just get a set of differential equations for the coefficients of the expansion of our state, right? We just substitute these guys in, we get a set of equations for the linear expansion coefficients. And that's pretty easy to write down. So these are just the E to the N delta and M plus W. We're basically just writing the Schrodinger equation in the basis of eigenstates associated with the unperturbed Hamiltonian. It gives us the set of differential equations. So just like in the Rabi part, remember in the Rabi part, we had this static magnetic field which induced a precession. Well, a very similar thing happens here is that there's the static part, which is the unperturbed Hamiltonian, which gives us these terms right here. This is from H naught. So what you want to do is go into the co-moving frame. Or in this case, it's not co-moving, there's not a rotating frame or anything, but we just want to change variables so that we get rid of that stationary part. But it's mathematically identical to getting rid of that static field by going to the co-moving frame. And these formulas should be sort of like deja vu or something. We define gammas, which are related to the C's, as follows. It's e to the minus I E N T over H bar gamma n T. Just a change of variables. And what does this do? This takes care of the evolution due to that H naught part, right? It gets rid of that En. So we can just substitute this in, right? We take this, plug it back into here. And what do we get? We just get well, yeah, En e to the minus I E N T over H bar gamma n plus I H bar e to the minus I E N T over H bar partial T gamma n. That's just the time derivative hitting the exponential and the gamma part. And this is all equal to sum over M E N delta M lambda W T. Oh, sorry, I'm gonna, of course, plug in for the gammas. Gammas are e to the minus I E N T over H bar C. Oh, this is now M C M. Oh, sorry. Gamma M, of course. Okay, so now you see that these guys are just going to cancel on the two sides of the equation. because this only picks out the m is equal to n term. So that'll just, these will just cancel out. And then things become a little bit more easier, a little bit easier. We can take this guy, this factor here, it's just a constant, and we can put it on the other side of the equation to get a pretty simple Schrodinger equation for the gammas. It's gamma n is equal to sum over m, and now it's only the w's that are left, and of course they're generally time dependent. And then we have e to the I omega n m t gamma m, where omega n m is just the frequency associated with the difference between en and em, right? Because we put the en onto the other side. And look, this is very nice, because now if lambda is small, right, then this whole side of the equation is 0. And so it means that the gammas don't vary very much, right? If lambda is quite small, then basically the gammas are going to stay close to their initial value. So that's kind of the idea. And when we do this more generally, this idea of undoing the time evolution due to H naught, that concept is called moving to the interaction picture. And so this transformation here, where we undid the evolution due to this H naught, that's essentially moving to what's called the interaction picture. And we'll talk about that more generally later. But first, I want to derive this Fermi's golden rule thing. So, okay. So now let's assume that lambda is small. And if we do that, then we can say, well, then gamma n as a function of t, well, then I should really be able to say that it's a delta function centered around the initial state I. So it's 0 everywhere unless n is equal to I, the initial state. And then there might be some small perturbation. We'll call it delta gamma n. So this is just a variable change. I haven't really done anything. But as I said, because these gammas don't vary much if the perturbation is small, then we can say, well, approximately it's just whatever the initial state is, right? That's just a single coefficient corresponding to that initial state, plus some small perturbation. So when we plug that in, what we'll get is I h bar partial t now acting on delta gamma n. Of course, the derivative doesn't do anything to the delta function. Then there's the matrix element associated with the ni here, t e to the I omega ni t. That's that term from the delta function, plus the rest of the thing, which is just there's the lambda e to the I omega n m t times the delta gammas. And the point here is that the delta gammas are going to be small. So this term is going to be small compared to this guy, because that guy is to do with the gammas just staying near their initial state. So we're just going to say, oh, fine, well, basically the idea is that this delta gamma, right, will itself be of order lambda. So then if you have a lambda times delta gamma, since the delta gammas are expected to be small, just from looking at this equation sort of self-consistently, then this term should be small compared to the first one. So it's a sort of leading order in lambda, roughly. We should get that this is just lambda w n I t e to the I omega n I t. And now there's no gamma on the other side. Now we can just integrate this, right? If we want it. And for Fermi's golden rule, what you typically assume now is you assume some form for the perturbation. And we're going to assume an oscillating perturbation. So what does that mean? And we're going to assume that W of t, of course, it's an energy operator, so it has to be Hermitian. So we're going to say it's A e to the minus I omega t plus A dagger, just to make it Hermitian, of I omega t. So so W is equal to W dagger, so it's Hermitian. The two terms just change into each other. So it's a harmonic perturbation, and A is going to be some time-independent thing. So we can now just integrate this equation and get our result for the delta gamma. And which gamma are we looking at? We're going to be interested in the gamma associated with the final state of interest. So we're going to gamma F. Because that's, remember, our purpose here is to calculate the transition between an initial state to a final state. So we're going to be interested in the expansion coefficient associated with the final state, F. We're assuming we're looking at eigenstates. Our initial and final states are eigenstates of our unperturbed Hamiltonian. You know, it's like looking at transitions between spin up and down in that Rabi oscillation problem, right? Remember there we calculated starting spin up, and we calculated what's the probability of spin down later. Those are both eigenstates of H naught. So again, we're going to, it's sort of implicit here, IF eigenstates of H naught. Okay, so good. So we can just start integrating this up. It's 1 divided by IH bar, the integral from, you know, the initial time up to the time we're interested in. Let me make this T bar or something. Of what? Well, of lambda W. And let's just call this lambda W. Let's just drop the lambda just to make things easier. Let's assume that lambda sort of absorbed into the A's. Well, we would have A, the matrix elements going from the final to the initial state of e to the minus I omega t and e to the I omega fi t plus the dagger business. The dagger is, of course, complex conjugate and transpose. We'll use that in a moment, but for now, let's just put it the matrix element fi of A dagger, and this is e to the I omega t, and again, e to the I omega fi t. You can sort of see hints of that Rabi oscillation stuff in here, right? Because omega is like our applied frequency. Omega fi is roughly like the Larmor frequency-ish. So it's got that flavor. So there'll be an associated kind of detuning and a resonance condition. But anyway, well, let's just go with the mathematics for now. So, okay, we have this. When we can do the integration, it's 1 over IH bar. These are just constants, so the the integral doesn't do anything here. This integration becomes minus I. I should put bars here because it's the variable of integration. I omega minus omega fi t minus 1 That's just from, and then there's, divided by omega fi minus w omega, right? That's just the integral, that first integral. It's just the integral of an exponential. Here we have a star, and now it's complex conjugate and transpose, so this becomes if. And similarly, we have e to the I omega plus omega fi t minus 1, all divided by I omega plus omega fi. That's again just from the integral. So yeah, so that's just doing the integration. And now nice stuff happens where, we can cancel some of these i's. All right, and this just becomes 1 over h bar a fi e to the minus I omega minus omega fi t minus 1. We pick up a minus sign, so this becomes this, and then this becomes minus a star if. Like that. And you see this delta gamma will be large when omega is equal to plus or minus omega fi. And that's kind of like the equivalent of the resonance condition. You'll get the most change in your state when your applied frequency is the same as the frequency associated with the transition between the initial and the final state. That's the idea here. When you drive with a harmonic perturbation, that's the same frequency associated with the transition between an initial and a final state, you'll get the most change in your state. You'll get the most probability of transitioning there. So we can actually calculate that explicitly, the actual transition probability from going to the initial to the final state. Well, that's nothing but actually just this delta gamma f squared, because this is the coefficient associated with the final state of the expansion of psi of t, assuming that we started with an initial state I. That's how we got here. We assumed that our initial state was I, and these are just the coefficients. Remember, the gammas are just related to the c's. So, and the c's, what were the c's? They were just the expansion coefficients of your state. So if we wanted to get this, that's like calculating CF, C subscript F, the coefficient of the final state term squared. But that's going to be just proportional to gamma F. And so this is the only part that you get. And of course, this also assumes that F is not equal to I. That your final and initial states are not the same. Otherwise, you'd get that delta function piece. So it's just this, and let's assume then that we're driving it at approximately on the resonance condition, under resonance conditions where our applied frequency is about the frequency of that transition. Then only this term will contribute, right? Because this will be very large when omega is equal to omega fi. And so we get a fi squared over h bar squared. And we can actually rewrite this as sine squared omega minus omega fi t over 2 divided by omega minus omega fi t divided by 2 squared. You can check for yourself that that's just the complex exponentials. When you square them, you can take this you can take top and bottom and multiply it by e to the plus I omega minus omega fit over 2. You get a difference between the two exponentials, and when you square it, you can just you'll get the sine function. And what is this thing? What is this funny function? It's really the function is sine squared of x over x squared, and that kind of looks like this. It's got small oscillations, and then it's got a big oscillation there. And as you make as you get closer and closer on resonance, what happens is that as omega approaches omega fi, this thing starts to be more and more sharply peaked at around the origin. This is omega really close to omega fi. And this thing starts to look like a delta function. And indeed, you can actually define it as a delta function, because you have the following integral. The integral of sine squared over x squared over pi is equal to 1. So you can actually interpret this guy as a delta function if you're close to the on-resonance condition. As you make omega close to omega fi, the limiting form of that function is a delta function. Because as this number gets smaller and smaller, basically all of the weight of the function will be concentrated around the origin. So this whole thing is approximately equal to 2 pi magnitude of this AFI squared and then we have so you got to be a little bit careful. There's going to be a factor of let's see. Yeah, so I'm missing. So there's a t squared here. I'm missing a t squared up here, right? Because t squared and t squared. So we introduce a t squared here so that this looks like sine squared x over x squared. So there's a t squared here that we had to introduce in order to do that. And this becomes delta omega minus omega fit divided by 2 over h bar squared. That's just approximating on resonance this sine squared x over x squared as a delta function. And then we can use properties of the delta function and extract out that t to get that this is 2 pi over h bar squared. If we factor out a t from the delta function, whenever you factor stuff out of a delta function, you have to divide by that number. So this just becomes, oh, sorry, and there's no 2 here. It's like that. So when you factor out a t over 2, you actually have to divide by that. So you divide by t over 2, so that you get the t over 2 there. And this is t squared still, and this is delta omega minus omega fi. And so one of the factors of t's cancel, and you get you get an expression for the transition probability. This is using the fact that a delta function has this property. Very important property for you to know. If you extract out a constant from a delta function, it comes in as 1 over the constant. Okay, so I'm out of time, but next time I will do a little bit more and talk a little bit about the kinds of final states that we typically look at. And the kinds of final states we typically look at are free states, which is the free particle, which is just a simple kinetic energy, not in the potential. So I'll talk about that a little bit and give the sort of final form of Fermi's golden rule. But this is basically the idea of Fermi's golden rule is already embodied in here, is that the transitions, the probability of transition is extremely enhanced right when you're on resonance between the initial and final state energy level difference. And it's proportional to actually a delta function of that resonance condition. And so we'll see how we can use that we'll go a little bit further and derive sort of the more common form of the Fermi's golden rule, but that's it for now. Any questions?